This video is about antiderivatives. Of course, we're in the context of calculus where we understand a derivative, both in its definition, with a limit, and even the shortcut formulas for a lot of the common functions. So now we're going to be going really just backwards with a lot of those formulas. We'll start our notes with the definition, which states this. Capital F of x is the antiderivative of lowercase f of x on an interval if capital F prime of x equals lowercase f of x for all x in that interval. Alright, so using familiar notation with the prime, what we're basically now just saying is that capital F is a function whose derivative is the lowercase f of x, and so it would make sense to say that if you go backwards, you could call capital F the antiderivative of lowercase f. Now we're going to add some things to this definition. First, a theorem. If capital F of x is an antiderivative of lowercase f of x on an interval, then the most general antiderivative of f of x, lowercase f of x that is, on that interval is capital F of x plus c, where c is an arbitrary constant. Okay, let's explore why this makes sense. First of all, catch some key language here. We said in this theorem, if capital F of x is an antiderivative, implying that maybe there is more than one, and capital F is just one of them. And sure enough, we talk then about the most general antiderivative, meaning there could be many. And let's see an example of how this works. If I take the derivative, I'll just say d over dx of just a general function, let's call it x cubed plus 2. We've done these kinds of derivatives many times already. This would be using just the shortcut power rule here, where the 3, the power of this x, would come down in front, making it 3x squared. We decrease the power by 1. But then, as we've seen, any constant term, when taking the derivative, would just turn into 0, which means the derivative is just 3x squared. We don't even write the 0. Okay, now alongside that, let's try another example, where this time we want the derivative with respect to x of, this time let's use x cubed plus the square root of 8. I'm just picking some random constant here. But the point remains that if I were to find this derivative, I would say 3x squared, again plus 0, which means 3x squared would be the derivative. Now notice, we're getting the exact same derivative, but it came from two different functions. Now they weren't that different, they simply had different constants. There was a plus 2 and then a plus square root of 8. Okay, the point is that those two different functions, when taking the derivative, produced the same result, this 3x squared, because when you take the derivative of a constant term, no matter what that constant is, it turns to 0, and that's why it doesn't even show up in the derivative. Now, because of this, when we're going backwards, which is what we do when we do antiderivatives, we don't know what that constant was if we're going backwards. Think about it. In these two examples, if I start at 3x squared and work my way backwards, this function was x squared plus 2, but this function was x cubed plus the square root of 8. So those two different constants that we come to when going backwards, we wouldn't have any way to know what those were if we didn't see the original function, or rather just the derivative. Because of that, when we go backwards, we will just call that constant that we don't know, the arbitrary constant, the letter c. Now, related to going backwards with derivatives, which is really what we're doing in antiderivatives, we already know lots of formulas or shortcut formulas for common functions derivatives. So, going backwards is really not much different. I'm going to say here, see the textbook for a table of common antidifferentiation formulas. There's a whole list of them, and they should correspond with the formulas we already know for derivatives. And we need to memorize these common functions. Now I'm going to be demonstrating some of those formulas or shortcut rules for antiderivatives in this video with some examples, but ultimately you want to make sure you go through and try all the various forms of formulas. No matter what textbook you happen to be using at this time, usually there's a table of these antiderivatives as well as derivatives. Usually they're kind of written side by side. You'll want to know all those formulas. Let's try some examples where we want to find the most general antiderivative of each function. Now when it says most general, that means we have to remember to put the c in the antiderivative. Okay, as we said in our notes above, there should be a plus c written with an antiderivative for the most general form. So let's see how that actually shows up with an example. Our first function is f of x equals 6x to the fifth minus 8x to the fourth minus 9x squared. I'm going to use the notation of capital F of x, since that's what we've used up in our notes here, given that this function was lowercase f of x, and we're trying to find the antiderivative of it. So capital F we will denote as the antiderivative of this lowercase f. And now I'm going to use some of the antiderivative formulas that you'd find in the list in the textbook, like in a table of a book. And so they're kind of like the same shortcut derivative rules we already know, but now going backwards. So with power function terms like we're seeing here, the rule for an antiderivative would be that you add 1 to the power. So instead of 6x to the fifth, I'm going to call it 6x to the sixth. But then when you add 1 to that power, you divide also by that new power. So it's 6x to the sixth over 6. Minus, same thing with this next term, we're going to add 1 to the power, so 8x to the fifth now, but then divide by that new power of 5. And then moving on, same thing with the last term, we'll write it as 9x to the third, increasing that power of 2 by 1, but then divide by that new power, so it's over 3. But then, of course, we'll go ahead and reduce. But before we do, let's go ahead and add our plus c. Okay, there it is. When we want the most general derivative, we have to put this plus c at the end, because remember, there could be some unknown constant there whose derivative would disappear when we take its derivative of this function to get this previously given here lowercase f of x, the derivative function. Notice we don't know what that constant might have been because it would turn into 0, which is why it doesn't show up in the derivative there. If I now go ahead and reduce all of my terms, I'll end up with x to the sixth, those 6's cancel, minus 8x to the fifth over 5, that doesn't really reduce, 8 over 5 there, minus, and then 9 over 3 is really 3, so we'll say 3x cubed, and then we'll have to say plus c. The good news with antiderivatives is that you can always check them by simply taking the derivative. If we take the derivative of this function we've now boxed in, we should get where this problem started, and you can always do that to check, which is actually a good way to practice knowing the formulas as well. Now I will say, it's often common for students to get confused about derivative and antiderivative formulas, so practice them. You'll have to keep writing them out perhaps until you memorize them. Check your answers. It's common to kind of get mixed up and go the wrong way with the formula, but you will be responsible to know them. Let's try a second example. Now this example is given as lowercase f of x equals, and then it's the quantity x minus 5 in parentheses that are all squared. Okay, now you may be saying, oh, we've done things like this, but it involved the chain rule, right? We've taken derivatives of stuff like x minus 5 in parentheses squared, where we take the power, throw it down in front, but then when we have a composite function like this, we've also been multiplying by the derivative of the inner function as part of what's called the chain rule. Okay, so I know that that's probably in your mind in a scenario like this. However, we're going backwards. We're not taking the derivative of this function. We're taking the antiderivative of this function. Because of that, there actually is a way to go backwards with the chain rule derivatives formulas, but it's a little more advanced and we're going to get to it, just not in this initial antiderivative formula video here. So until we get to the way to go backwards with the chain rule, we're simply going to go a simpler route, which is let's just rewrite this function given as x minus 5 all squared, but by expanding its terms. Remember, this is really x minus 5 times x minus 5 if it's x minus 5 squared, which means we could really just write this out without too much trouble as x squared minus 10x plus 25. It's a simple expansion. Now, if this power was way higher than 2, like even the cube, we could do, but then it's getting a little annoying. If it were any higher than that, for sure, we would want a better way to handle this, and that's what we will eventually get to if we were to treat it as a composite function. But for now, we're just going with the simpler route, so we expanded what we have. Notice now it's just 3 terms. It's a polynomial power function kind of antiderivative. So we can say now that capital F of x, the antiderivative, using really the same rules that we used in the first example, which would be the power rule going backwards, we're going to add to these exponents and then divide by those new powers. So x squared will turn into x cubed and then divided over 3. Okay, so moving on, minus 10x squared over 2 plus 25x. Now, you could call it x to the first over 1 if you'd like, and there's a couple of reasons to think of it that way. Number one, really 25 is like 25x to the 0, but we normally don't write that. You just see the constant 25. Okay, but when going backwards, you could think of it as adding 1 to that power, which would give you x to the first over 1, but we know that's trivial. The 1 doesn't do anything, so you can just call it 25x. But then do not forget we have to put our plus c at the end because we don't know what arbitrary constant could have been lurking in this function, such that when we took the derivative we got this given f little lowercase f of x, and of course that constant would have turned to a 0 there. So we have to put the plus c for the most general derivative. Let's try a third example. This one is given as lowercase f of x equals secant of x tangent of x minus 2e to the x. Okay, so as you are probably thinking already, when you look at that chart of derivative rules that we've already used, we're basically just going backwards with them. And so you'll start to hopefully recognize some familiar derivatives that we've already been using, but we're just going backwards now. So we're going to say capital F of x equals, and now the first term was this secant of x tangent of x. You'll recall that that is a derivative, and in fact that's the derivative of secant of x, which means if we're going backwards we want the antiderivative of secant tangent, which is just secant. So again, it'll take some practice to get these derivative and antiderivative rules all ironed out and memorized, but the more you practice them, the more familiar they'll get. Moving on to the next term, we'll say minus, and then remember that constants don't actually affect derivatives. Like this 2 in front of the e to the x wouldn't be affected or involved in taking the derivative of something that would give me that term. So we're going to leave the constant there in front as well when going backwards. Now, the derivative of something here has to give me the e to the x. Well, again, if we recall our derivative formulas, you know that the derivative of e to the x is e to the x. And so I can just call this second term minus 2e to the x, which is no different than it was in the derivative. And again, if you want to refresh or be sure about that, imagine taking the derivative of this function as we see it now. You should be able to get this function given as its derivative, since we're going backwards. Okay, so now we have these two terms, but we must put a plus c for our arbitrary constant, which gives us now in total the antiderivative. Let's move on to a fourth example. This one is given as lowercase f of x equals 2 cosine of x minus, now it's a fraction which has 3 in the numerator, over the square root of 1 minus x squared. Alright, so let's recall our derivative formulas and try to use them backwards, which are really the antiderivative formulas, and think of which function would have a derivative equal to this first term, which is 2 cosine of x. Well, you'll recall that the derivative of sine of x is cosine of x, And if I had a 2 in front of the sign of x, trying to think backwards here, then that 2 would actually stay in front when taking the derivative of this term. And I would just have 2 times the derivative of sine, which is cosine, which is what I want. So the first term in the antiderivative must be 2 sine of x. Okay, so again, you can just kind of think backwards with antiderivatives and derivatives, and hopefully you'll get them all matching. Now, as we go on to this next term, let's recognize something familiar in it. If you first of all take, let me just kind of rewrite this for a second in a way that's a little more familiar. Wouldn't 3 over the square root of 1 minus x squared really be 3 times 1 over the square root of 1 minus x squared? Right? Fractions would enable that to be written that way if we'd like. But that helps us recognize that really this 1 over the square root of 1 minus x squared, that's a familiar derivative, which means if I'm going backwards for the antiderivative, we can think of this as 3. That constant would just stay in front, but then we could recognize this second factor here, this ugly fraction, as the derivative of the inverse sine function. So you could call this antiderivative sine inverse of x, or sometimes you might see it written as arc sine, same thing, different notation. But that's the antiderivative, and then we'll say plus c for this arbitrary constant, which now gives us the full antiderivative of this original function. Let's try another example, but this time we're going to change it up a little bit. This one says, find lowercase f given the following conditions. Okay, so what we know first is that lowercase f prime of x equals x plus 1 over x cubed. Okay, that's one condition, comma, x is greater than 0, comma, f of 1 equals 6. Okay, so notice what's going on. We're doing a slightly different notation here. This time, what we're given is written as f prime of x, and we want to find f of x. So that's antiderivative notation, where, of course, the prime is the derivative, and the simple f would be the antiderivative. So really that's what we've been doing. Let's go ahead and try to do that, but I'm going to write it out slightly differently. I'm going to recopy our f prime function here for a second, but write it as x plus x to the negative 3 power, which is really what this function is algebraically, but I'm trying to give us a little help on using this power rule backwards here since we're new to it, okay? So f prime is really this. We're looking for f though. So let's go ahead and say that f of x, which is now the antiderivative, we've been using capital F for this, but now we're just kind of sticking with the prime and simple f notation here. We're going to use the same power rule going backwards, so the antiderivative of x would be x squared over 2, that is, increase the power by 1 and divide by the new power, plus, now we're going to do the same power rule going backwards for this next term, but when I add 1 to its power, now it'll be x to the negative 2, and then I divide by that new power. So we're adding 1 to negative 3, which gives us negative 2. Okay, that can be a little confusing at first. Make sure you practice that. And then, of course, we'll say plus c at the end for our arbitrary constant. Now, we want to clean this up a little bit and incorporate the fact that we have more information given in this problem. Simply by putting a plus c here at the end of this antiderivative, as we said above in our notes, that accounts for the most general antiderivative. In other words, we don't know what c is, but we know that no matter what it is, any arbitrary constant, if I were to take the derivative of this f function, I would get the f prime function because that constant's derivative would turn to 0, and sure enough, there's no constant written in the derivative there. But because of that, this with the plus c in it is what's known as the general solution. And there's value to it. That's what we've been getting so far. But given other information that we have in this problem, we can actually go further. So notice that it says, first of all, x is greater than 0. Now that simply means we're stuck on the right side of the y-axis, or you could say we're only dealing where positive x values occur. Of course, given the way this function is defined, f prime of x here, It's not defined at 0 because we'd be dividing by 0 there, right? So the f prime is not defined there. Even f is not defined at 0 for the same kind of reason in the second term. So we're just sticking to where it's defined, where x is positive. But then secondly, we say that f of 1 is 6. Now notice that's just a plain f, which is exactly what we've been finding. So if f of 1 is 6, then what that tells us is that I can say 6 equals, and then I can plug in 1 for x in this antiderivative formula that I've been constructing already. And so I'll have 6 equals, really it's 1 squared over 2 instead of the x squared over 2 that we had previously. And then it's 1 to the negative 2 over negative 2, again for that second term up there, and then plus c. But notice now, this is an equation where we could actually solve for c. So let's do that by simply crunching this out. We'll have 6 equals 1/2 plus, this would become negative 1/2 plus c. This second term arithmetic, if you simplify it, is just negative 1/2, which means these the plus 1/2 and the minus 1/2 just cancel out, which means 6 equals c, which means if we know c, we can put it in place with this general solution and say that f of x equals x squared over 2, and then really we should say minus 1 over 2x squared. That's coming directly from what we had in the general solution, those first two terms. But now if c is 6, I can say plus 6, and this will give me what's known as the particular solution. And it's particular because it's using the extra conditions given. Let's try another example. This time we're given that f prime of x equals 3 to the x minus 3 over x. Okay, so that's given as a derivative, thanks to this prime notation here. But then we're also given that f of 1 equals 2, and that f of negative 1 equals 1. All right, let's figure out why we might need all of these pieces of information to get this going. If I want to try to find the antiderivative, which we'll just call it f of x, knowing that the prime notation was used for the derivative there, then we want to work backwards. Now this is going to have to cause us to drag through some of the other derivative formulas we know and try to use them backwards. Of course, this could also be found in the chart which shows common derivatives and antiderivatives of common functions here. But what we can say is this: the antiderivative of 3 to the x, which by the way is an exponential term, would be 3 to the x over the natural log of 3. Okay, so that's coming from those formulas in the chart. And again, you can check that by taking the derivative, which would require you to know how to take the derivative of a exponential term like this. But if you do, you'll notice that the derivative of this 3 to the x would have a natural log of 3 pop out of it, which would then cancel with this one below and give us what we're given here as the derivative. So you can see it all fits together. It just takes some back and forth practice to be confident with that. Let's keep moving. Now, you'll also recall that the next term has this 3 over x. That constant of 3 can just stay there out front. But then you'll also note in the antiderivative chart that the antiderivative of 1 over x, which is really what we have here, turns out to be the natural log of, careful here, it's the absolute value of x. We have to put that absolute value there as part of that formula, and then we'll say plus c. Now here's where this example gets interesting. This natural log of absolute value of x that we have here necessarily as part of our antiderivative, really, if we understand what that means, recalling absolute value, it could be defined as a piecewise function where you have the natural log of x, but that's only in the case where x is greater than 0. Otherwise, it's the natural log of negative x, and that, of course, is if x is less than 0. And because of that, we actually have to define our antiderivative in terms of a piecewise function to encapsulate all of this information together. So we're going to say f of x, the antiderivative that we've already started, is going to be defined as a piecewise, where the piecewise split of this natural log term is going to kind of be what determines our pieces, but they both get this original first term here we have of 3 to the x over ln 3. So we're going to call the pieces 3 to the x over ln 3 minus 3 times natural log of x. That's like this first case of the piecewise function there, but that's only for when x is greater than 0. Otherwise, our antiderivative is going to be 3 to the x over natural log of 3 minus 3 ln of negative x, and of course that's for when x is less than 0. Now you'll notice that I kind of left off this constant plus c here. That's because really these two different pieces now that we're getting when we split this thing would each have their own constant. So we'll call the first one maybe the plus c that we had originally, but then I'm going to call the second one plus d. We just got to use something different. Sometimes you'll see books use like c1 and c2. Okay, it doesn't really matter, but they have to be two different constants. Perhaps now you can see why we needed so much initial information given. So if we go back and use the rest of the pieces that they gave us, recall that f of 1 was given as 2. So if we use that information, we'll get one thing. But then we were also given that f of negative 1 equals 1. Okay, so those are kind of each using different pieces here. So if f of 1 is 2, okay, f of 1, that would fit into where x is positive. Okay, and so if we go ahead and use that piece, we can say 2, that's the output there, equals, and then it's going to be 3 to the 1 over the natural log of 3 minus 3 times the natural log of 1 plus c. So we have to solve this for c now, which would give us 2 equals 3 over the natural log of 3 minus, now natural log of 1 would actually be 0, which means that whole term would just drop out. So that's gone. That's 0, I could say, or equals 0. And then that's plus c. So really we could say here that c is 2 minus 3 over the natural log of 3. Okay, now moving on to the next case. We know the output is 1 there, so we'll say 1 equals, and then it's going to be 3 to the negative 1. We're plugging in now negative 1 for x. 3 to the negative 1 over the natural log of 3 minus 3 times the natural log of 1, because notice if you plug in negative 1 to x, but it was already negative x, that's like saying negative negative 1. Let's take this a step or two further. If we rewrite again, we'll have 1 equals, and then the 3 to the negative 1 will really become a 1 over 3 times the natural log of 3. And then this natural log of 1, of course, that's 0, so that whole term drops out, kind of like happened in the previous case here. And then plus a d. Now we can clean this up a little bit, so let's call this, if we solve for d here, we'll say d equals 1 minus, and then you could call it 1 over 3 ln 3, or you could pull a natural log trick on that. Instead of 3 ln 3, you could call it the ln of the natural log of 27, right? Because you could take that power, or that 3 in front, and make it the power of the 3, so 3 to the third is 27. So really either way is fine, but that gives us now the two constants needed for this antiderivative, which means we can now summarize the particular form of the antiderivative, now that we know the constants, and call it f of x, that's what we had started with above, equals, and then we're going to define this antiderivative as a piecewise, where the first piece is going to be 3 to the x over the natural log of 3 minus 3 natural log of x plus 2 minus 3 over the natural log of 3. So there's the c value showing up that we had just solved there, but now it's all written out, and then we could say this is only where x is greater than 0. The second piece would be 3 to the x over the natural log of 3 minus 3 natural log of negative x, and then plus 1 minus 1 over the natural log of 27, again in keeping with the d constant that we had found, and that was when x was less than 0. So in summary, this huge piecewise function would be our antiderivative. Let's try one more example. This one says if a of t equals t squared minus 4t plus 6, and s of 0 equals 0, and s of 1 equals 20, find s of t. Now, in order to get this one understood, let's recall some key things. We've seen this kind of notation before. Recall that s of t is position, and therefore s prime of t equals v, velocity, and then v prime of t, v is velocity, so v prime of t would be acceleration, which is a of t. So in this problem, when we're given a of t, and then s of different things, and looking for s of t, we're talking about this context here. So they give us a of t, notice that's acceleration, but they want s of t, which means we have to work our way backwards doing antiderivatives. So let's use that understanding of the relationship between all these different qualities or characteristics, acceleration, velocity, and position, and understand that I could start by saying v of t, which by the way is the velocity, is the antiderivative of a of t, which is the acceleration that they gave us. So I can just use the antiderivative of that, and in the same way we've been doing, get t cubed over 3 minus 4t squared over 2 plus 6t plus, and I'm going to call it c1. Notice that they don't actually give us any of the givens that involve v of t, which means we can't plug in these known quantities to find c1 here yet, so let's just keep going. We know we're trying to work our way back to s of t, which would then be the antiderivative of v of t. So let's say here s of t equals, now we're just doing antiderivative of this velocity equation we just got, which means same thing, add 1 to the power, so now it's t to the 4th, but then divide it by that new power. Now it was already a 3, so I'd be now multiplying that 3 by the 4. So be careful with that arithmetic there. I'm going to leave it like that and simplify it later on here. Keep going though, we'll end up with 4t cubed, increase that second power by 1, but divide also by it, so now it's 2 times 3 in that denominator. Okay, and then moving on to the third term, it was 6t, now it's going to be 6t squared over 2, and then it was plus c1, so it's going to be plus c1 times t, and then plus, we'll call it c2. Let's go ahead and just simplify the position s of t equation we just got from our second antiderivative here before we start plugging stuff into it. So really it's t to the 4th over 12 minus 4t cubed over 6, but you could reduce 4 over 6 is really 2 over 3, let's just write it like that, and then plus 6 over 2 is really 3, so really it's plus 3t squared plus c1 times t plus c2. Or instead of using c1 and c2, you could use c and d. The point is they have to be different constants. Now let's recall the other givens. We knew that s of 0 was given as 0, and we knew that s of 1 was given as 20. So we can use these to find the missing pieces. If s of 0 is 0, I'm going to plug in 0 for all the t's in this s equation we just got, and then going through, of course, that would mean we have 0 minus 0, that's the first two terms, plus 0 plus 0 plus c2. Okay, so that's just plugging in 0 for t's in this s equation we got. But of course, this is all equal to 0, supposedly. That's what s of 0 is supposed to be, which means then we can say c2 must be 0. Alright, so that's one of the values we need. Let's move on to the next condition where when t is 1, the output is 20. The output for the s function, that is. So let's now say plugging 1 in would give us 1/12 minus 2/3 plus 3 plus C1 plus C2, but we already found C2 to be 0, so we can just plug that in as is. And then this is supposed to equal 20 as given here. If we solve this for C1, which is really just a bunch of arithmetic, you could use a calculator to help with that, we should get that C1 is 211 over 12. Okay, I'm sparing you all the arithmetic, but that should be the value we get, which means in summary, we can say s of t, our position function that we were looking for, should be t to the 4th over 12 minus 2t cubed over 3 plus 3t squared plus c1 times t. Well, again, c1 we found to be 211 over 12, so it's that times t, and then plus c2, but we said c2 is 0, so really you don't even need to put the plus 0 on the end. We'll just box this up as our answer for s of t and leave it right there. This would be the particular solution given those conditions in the beginning.